Lab 4, Oscillations. The purpose of this lab is to model the motion of the spring mass system using Newton's second law of motion and the energy principle. The main result of this lab proved that predicting the motion of the spring mass system was much harder than expected, possibly due to air resistance and heat transfer. In this lab, we used Newton's second law, V final equals V initial plus F net divided by mass times change in time, and the energy principle, that the change in energy is equal to the change in kinetic energy plus the change in potential energy. If the change in energy is equal to zero, the energy principle is satisfied. If we watch the motion observed in Tracker, we can see that the position of the mass changes in both the x-axis and the y-axis. After finding these positions, I created a CSV file of the x and y positions to use as a comparison to the model in Python. In a system of the mass by itself, the net force equals the weight force, negative mass times gravity, plus the spring force, negative spring stiffness, times the displacement times the orientation. To predict the motion of the spring mass system, we need the spring stiffness K. To find K, we can rewrite the formula for one period of oscillation, called T. However, we need to find what T is first. To find the best estimate for T, I use 5 oscillations, where 5T equals 8.26 seconds. So T equals 1.652 seconds. Now that we have the spring stiffness K, we need to find the relaxed length of the spring, L naught, to find the spring force. To do so, we know that the weight force and the spring force are equal, so we can set mg equal to Ks. Then, using the formula for S, we can find that L naught equals L minus mg divided by K. Now, using the given mass and gravity, and what we found T to be, we find that K equals 5.82 newtons per meter and L naught equals 0.037 meters. In the code, I plugged in the mass in the initial position and calculated the initial velocity using the first 2 data points from Tracker. Next, I plugged in the rest of my data into the code along with the equations for the calculations and ran the model. The first model shows the comparison of the positions from Tracker and the predicted positions, while the second model graphs the energy. In this model, the blue ball represents the model predictions and the red ball represents the Tracker positions. In the second model, the blue line represents the change in kinetic energy, the red line represents the change in potential energy of the spring, the green line represents the gravitational potential energy, and the yellow line represents the total change in energy. The first what does it mean question asks, is the energy principle satisfied? As you can see from the last model, the energy principle is satisfied because the total change in energy, the yellow line, is equal to 0. The second what does it mean question asks to make 2 separate estimates of oscillation periods, one from the x position data and one from the y position data. As I explained earlier, I used the y position data to find the oscillation period before using 5 oscillations and found that T equals 1.685 seconds, K equals 5.82 newtons per meter, and L naught equals 0.037 meters. The comparison model and the graph turned out to match decently well, but the Tracker motion slowed down while the predicted motion remained constant. Next, I found the oscillation period from the x-axis data using 5 oscillations to find T equals 1.615 seconds, K equals 6.357 newtons per meter, and L naught equals 0.0525 meters. The graph using this data is much more inaccurate than the graph using the oscillation period from the y-axis. As a result, the data using 5 oscillations of the y position data was the closest estimate for the spring mass system motion. Although that data provided the closest graph of the motion, the Tracker motion slowed much faster than that of the predicted motion, which remained constant. 2 possibilities for this slowing down include air resistance and heat transfer as the spring stretches and compresses.